Welcome. This question says a pipe has an entrance area of 8 square meters. It has an exit area of 2 square meters. Water flows into the pipe at 5 meters per second. At what speed does water flow out of the pipe? So again, I like to visualize my own visualization so I can make things simpler or more clearer. So in this case, this is A1 and this is A2, and then this is my V1, meaning velocity, and this is my V2. And there's a relationship between these things. Basically, when I have incompressible water or incompressible fluid flowing into a pipe, the volume per second entering the pipe must always be equal to the volume per second leaving the pipe. If that were not the case, then you'd either have water getting to a higher density because you have more water in the pipe than you should have, or you'd have gaps in the water or low density water. And the density of the water is incompressible, or the fluids are assumed to be incompressible, so the density should be constant. So we can visualize a kind of volume of fluid there entering and in 1 second, and a volume of fluid there leaving, and they should be the same amounts. And we can say, well, volume is equal to an area times a velocity. That's not obvious, so let's just think about that. That is units of meters cubed, and area as units of meters squared, or square meters, and velocity is meters per second. So I'm sorry. let me step back just a little bit, because that doesn't work out. Volume per second, the amount of the volume of fluid entering is the same as the volume of fluid leaving, and that is given by the area times the velocity. And I can justify that by saying this is meters cubed per second, and that would equal, well, meters squared for the area times meters per second. So that gives me meters cubed per second. So everything's happy. The equation is called a continuity equation, and what it says is that A1 V1 is equal to A2 V2. And what I notice as a teacher is by the time this section comes in the course, people sometimes are getting tired and maybe they're a little bit disconnected, and so they're just relying on equations and trying to figure out what's going on. And when you're not paying close attention to detail, you know, is that V a volume or is that V a velocity? And you know, I can give you enough information in the prompt that you could hang yourselves on it. So it's not only important to know the relationships, it's not only important to know the equations, but you should also know what every letter in an equation stands for, and not just make mistakes like that. So returning to this problem, however, our entrance as a volume of, as an area of 8 square meters, and our velocity is 5 meters per second, and that equals, well, that's going to be my exit area, which is 2, and my exit velocity is what I want. So V2 is equal to 8 times 5 over 2. V2 is equal to 20, and of course it's a velocity, so it needs to be meters per second. Very simple. If you don't know the relationship, it's not simple. How can I make it more interesting as an examiner? Well, I don't have to give you the areas in the standard units. I can give you the areas as square centimeters or square millimeters. I could give you the shape of the entrance if it was circular and give you a radius for the entrance and the exit. I could make it a non-standard shape. I could make it triangular or octagonal or whatever I choose. I can just make it that little bit more interesting. I can play with this. It's important that you have the basic understanding of the continuity equation and then be able to deal with these other distractions as I throw them at you. You know this principle. If you're trying to wash your car using a garden hose and you want to get the water to stream further, you put your thumb over the exit of the garden hose. By putting the thumb over the exit of the garden hose, you reduce the exit area, and that therefore increases the velocity of the exiting water, which increases the momentum per drop, if you like, etc., etc. So there we have it.